Hello everyone, I'm Mohammad Washik Al-Azad. I am currently pursuing my PhD degree at the University of Nebraska at Omaha. Today I'm going to present our paper, Reservoir, named data for pervasive computation reuse at the network edge. Here is the outline of my presentation. I will start with the research problem we are trying to solve and what are the novelties of our proposed framework. I will also briefly discuss some background related to the proposed framework. Then I will present the design of the reservoir and how we evaluate it. And finally, I will finish my presentation with some key observation from the evaluation. Let's start with the research question we are trying to answer. Our main research question was, how can we build a framework for a distributed edge network to realize in-network competition reuse? If we break down our research question, then we'll find a few key points from it. The first one is lightweight. That means the framework should not impose a large overhead on the user device or on the network. The second one is distributed nature. That means because of fault tolerance, high reliability, better load balancing purpose, or some other reason, there will be multiple servers that provides the same service. And the last one is in-network awareness of competition reuse. That means since there will be multiple server, why should a task be forwarded to maximize the chance of competition reuse? Now, some of you may not be familiar with the term competition reuse. So let me give a brief overview of it. Nowadays, there is a number of devices such as smartphone, AR/VR devices, IoT devices, and usually they are close to each other and being used for similar purposes, which means they may ask for similar computation to an edge service provider. But the edge is a small scale network and has limited resources. One way to reduce the required computation at the edge servers is to identify requests with similar input data and reuse cached results instead of executing from scratch. If we are able to do that, then it will improve the response times, the limited resource will be utilized efficiently, and as a result, the capacity of the server will increase. Now let's see some use cases. Every year, millions of people visit the Statue of Liberty and take pictures of the same site from different angles or different distance. They upload these pictures as the input of the task for a service at the edge, which then identifies this site and returns information or content related to it. These pictures are similar, so the output result will be the same. Another use case is a traffic monitoring system in a smart city where each CCTV camera takes multiple snapshots per second. Now, the subsequent snapshot should be very similar to each other and may result the same output. Another use case can be that an edge network provides multiple services which has different results but have some common components. The common components of these services can have the same result with the similar input data. Now the question here is how our proposed framework is different from other prior work. Competition reuse can be achieved at the user device, at the edge nodes, or in the network. Here are some proposed prior framework for competition reuse. Crashia primarily focus on cache optimization mechanism at the edge node, where Potluck focus on the cache optimization at the user device among multiple applications. Foggy Cache explored the reuse of computation at the edge server across different user devices. Coterie is application specific and limited to the user devices. ICS is a proposed framework on top of named data networking, which mainly provide computation reuse at the edge servers. It also provides limited computation reuse at the user device and within the network infrastructure. On the other hand, our proposed framework Reservoir provides a universal design that can be used by all the application and exploit computation reuse at the user device, at the edge nodes, or in the network. Our framework Reservoir runs top of the Endian. So let's get a quick overview of Endian. Endian is a name-based communication model in which the client sends a request for data with a name. Then the request is forwarded based on the name in the request by the Endian network toward the server. When the server receives the request, it responds with the data packets. When the routers forward the data packets toward the client, they cached this packet to satisfy the future request for a data with the same name. Our proposed framework also uses locality sensitive hashing as a way to identify tasks with similar input data. In cryptographic hashing, the hash function tries to avoid the collision and yield an unique output for each unique input. But locality sensitive hashing does the opposite of the cryptographic hashing. If two inputs are similar to each other, then there is a possibility that the locality sensitive hash function generates the same hash value for both inputs. Here is an example of hash values of two subsequent snapshots for the cryptographic hashing and the locality sensitive hashing. The cryptographic hashing generates two different hash values, where the locality sensitive hash generates the same hash value since the subsequent snapshots are very similar to each other. As we are now familiar with Endian and locality sensitive hash, now the question arises, why do we use them in our design? Because locality sensitive hash can be used to label the request with similar input data as the same. And the second advantage of locality sensitive hash is that it can reduce the search space for reuse at the edge nodes. And as a result, the search process at the edge node will not cause large overhead. On the other hand, we can forward tasks with a similar input by using locality sensitive hash in Endian network. Also, Endian provide built-in in-network caching mechanism, which can be used to achieve reuse within the network infrastructure. So how can we build a framework top of Endian and locally sensitive hash to achieve pervasive computation reuse? To do that, we can use locally sensitive hash to identify similar tasks in the network and fast search for similar tasks. And we need to extend the forwarding pipeline of existing Endian to achieve computation reuse. We set a few design goals for our proposed framework. The first goal is minimum overhead for user device, and then the minimum overhead for the network. Also, a fast search process for reuse at the edge nodes. And the final goal is the framework has to be realistic for deploying in a distributed edge network. Reservoir works in 3 steps. In the first step, the user performs locality sensitive hash on the input data and then upload the tasks. After that, the Endian network forwards this task toward the edge node based on the hash values. In the final state, first, the edge node search for similar previously executed tasks, and if any match, then the result is reused. Otherwise, the edge node execute the task from the scratch. Now let's consider some task offloading mechanism where there is no task or result cached in the network. In the first scenario, the user uploads a task and the edge network searches and finds a match for reuse. Then the edge node responds with the reused result. In the second offloading scenario, the user uploaded a task to the edge node, but there is no reuse. So the edge node starts to execute the task from scratch, and the result will be requested by the user once the task is executed. In the last uploading scenario, the user wants to upload a task with a large input data. So the EN requests the input data from the user by sending one or more interest, depending on the input size of the data. Once the input is passed to the ENs, the execution will begin, and the user will retrieve this result once the task is executed. So far, we talked about how to do reuse from edge nodes. Now let's talk about how to do it from the network. To do that, we need to extend the way Indian network works. To this end, we introduce reuse FIB or RFIB. RFIB is a data structure similar to original Indian FIB, but it makes a router aware of reuse semantic direct in the network so that similar tracks are forwarded to the same edge node and reuse is facilitated. A RFIB consists of the service name, is node prefix, which buckets are assigned to a particular edge node, and output and index size. Let's consider an example of where a CCTV camera takes 2 snapshots and hash these subsequent snapshots. Let's consider 3 tables are being used to increase the accuracy of the framework. Now, 2 of the 3 hash values indicate that this snapshot should be forwarded to the edge node 1, but the other hash value indicate that they should forward it to the edge node 2. So that task will be forwarded with the majority of the hash value indicates. That means to the edge node 1. To achieve a reuse awareness in the task forwarding process, we extend the Indian interest forwarding pipeline for reuse. This will add a forwarding hint to the task request. A forwarding hint is just another name that indicates that to which edge node a task should be forwarded. This is added by the first router that also do RFIB lookup to determine that. In this way, we will do RFIB lookup only once along the path from the device to the server, and we minimize the overhead of introducing reuse awareness in the network. So far, I talked about the design of our proposed framework. Now let's talk about the performance evaluation. We evaluate the framework of Reservoir in 4 phases. In the first phase, we benchmark the component of the framework. In the second phase, we do experiment with the prototype. And in the third phase, we use network simulation. In 4th phase, we compare the result of Reservoir with ICS. We used some popular dataset and created a couple of datasets for our experiment and evaluations. This dataset has different correlation between the data and processing granularity. Some of them are fine grain, some of them are coarse grain. From the benchmark result, we can see that RFIB incurs minimal additional overhead compared to the processing of an interest through FIB. Also, with low-end user device, the required hash time is below 2 milliseconds, and the search time is lower than a millisecond for up to 100,000 images. Also, we can see that the RFIB size is less than 55 megabytes, even for a large number of services, is node prefix and locality sensitive hash tables. To evaluate the performance of the prototype, we deployed it on a small-scale testbed, as shown in the figure. The result shows that the reuse direct from the network reduced the task completion time up to 21x, and reuse from the edge node reduced the time up to around 6x. We also used a performance measurement matrix called reuse accuracy, which means if a task is being executed from scratch and if the task is reused from previously cached result, and if they yield the same output, then it's accurate. And we also achieve around more than 90% reuse accuracy. At the third phase of the evaluation, we use network simulation to scale up. We used 50 different realistic topologies, and the simulation result demonstrated the same trend as the experimental result of the prototype. At the last phase of the evaluation, we compared our proposed framework to ICS. The reason we compared our framework with ICS is that ICS is the only framework which is close to what we are trying to achieve through our proposed framework. From the result, we can see that ICS causes more forwarding overhead than our proposed framework, since ICS employs both name-based lookup through FIB and a specialized forwarding mechanism per application. We can also see that reservoirs achieve about 24% lower task completion time than ICS, since reservoir takes full advantage of in-network caching to retrieve the result of similar tasks from the content store of the forwarders whenever it's possible. Also, we can see that Reservoir achieved around 26% higher reuse accuracy than ICS. The reason behind is that ICS identifies reuse opportunity only through naming semantics. As we conclude, let's see if we are able to meet our design goals. From the benchmark result, we have seen that the hashing time is less than 2 milliseconds for the user's devices. Also, there is a minimal forwarding overhead for the routers. Then our proposed framework can search up to 100,000 images within less than 1 millisecond. And finally, we deployed the prototype on a small scale testbed. That means it is realistic to deploy the proposed framework in a distributed edge network. Thank you very much for your time. Let us know if you have any questions.